Okay, so in our last video we saw how to implement how Grover's algorithm works, and we showed that it requires order square root n iterations. But then what we also assumed is that we had two primitives, and one was phase inversion. So in phase inversion, what we do is we are given some superposition over over our entries from 0 to n minus 1. One of which is special, so we are given this function from this domain of size n, a Boolean function, so it maps it to 0, 1. And we are assuming that this function evaluates to 1 for exactly one such x. This is the needle in the haystack. This x is, we are calling it x star. And what we want to do is we want to implement phase inversion, by which I mean, well, you look at the amplitude of x star and you multiply it by -1. Okay, so that's what we want to actually implement. So how do we implement this this primitive? Okay, so first remember what we're actually given is a quantum circuit, which on input x and 0 outputs x and f of x. Actually, you could, maybe it's even better to think of this as on input x and b. So if your answer bit is b, then you get b exclusive or f of x. So your answer bits gets toggled if and only if f of x equal to 1. So now what we'd like to do is we'd like instead of getting the output bit, what we want this circuit to do in effect for us is we'd like it to map x. So this is what our ideal circuit does for us. What we wanted to do is map x to -1 to the f of x, x. Right? So remember, f is a Boolean function, and we are saying that f of x is 0 for almost every input. The only input on which f of x is 1 is the needle, x star. Okay, so now if we could implement this kind of a quantum circuit, then of course what it does is, if we give it as input summation over all x of alpha x, x, what do we get as output? Well, we get as output summation over all x of -1 to the f of x, alpha x, x. Right? But now we are saying f of x is 1 if only for the needle, x star. And so what this would do is it would invert the phase only of the needle, which is exactly what we wanted. So how do we carry this out? Well, remember what our observation is. Our observation was, okay, so this is our main observation, that if you take this function u sub f, this circuit u sub f, you input x, and instead of inputting this bit b, you input this bit b in the state minus. The claim is what this outputs is x minus, but with a phase of -1 to the f of x. Okay, so where does this phase of -1 to the f of x come from? So remember, what u sub f does is it toggles the output bit, the answer bit, if and only if f of x equal to 1. So if f of x equal to 0, it leaves the output bit alone. If f of x equal to 1, it toggles it, it switches it. So now what does it do to the minus state? So remember, minus is 1 over square root 2 0 plus 1 over square root 2 1. So there are two cases. So case 1, f of x equal to 0. If f of x equal to 0, it leaves the answer bit unchanged, so minus gets mapped to minus. Case 2, f of x equal to 1. In this case, the answer bit gets toggled. Sorry. Minus was 1 over square root to 0 minus 1 over square root to 1. Okay, now let's look at case 2. F of x is 1. It toggles the answer bit. So if the answer bit was 0, it gets mapped to 1. If it's 1, it gets mapped to 0. So what does minus go to? So now minus gets mapped to 1 over square root 2. So 0 gets mapped to 1, and 1 gets mapped to 0. So this is equal to, well, this is the same as the minus state, but with a phase of minus 1. Okay, so the phase you get is plus in the case f of x equal to 0, and minus in the case f of x equal to 1, which is exactly minus 1 to the f of x. So that's what we were looking for. Okay, so the circuit to do phase inversion is exactly this. So you just use the circuit for quantum circuit for computing f, except in the answer bit, instead of having it start at 0, you have it start in the minus state. So very simple. Now how about reflection about the mean? So what was this reflection about the mean operator? So remember what we wanted. We started with some superposition over our domain from 0 to n minus 1. And now let's compute, we are letting mu be the average of the alpha sub x's, right? So we start with some superposition, sum over x of alpha sub x, x, and we let mu be summation of alpha x divided by, I guess there are capital N elements. And now what we want the new superposition to be after the reflection about the mean is, well, each amplitude, if it's above the mean, it goes as much below the mean as it was above. If it's below, then it gets reflected and goes above. Right? So we want the new superposition to be sum over x of 2 mu minus alpha sub x, x. Okay. So how does, what kind of circuit implements this? So actually the circuit to implement this is very simple. So all you do is you take your n input bits, you first do a Hadamard transform on them, then you put them through a circuit. Okay, so this is x, this is minus. Okay, so same trick as with the phase inversion. But now what this circuit does is it's supposed to output. Okay, so this is computing the function f, so it's computing the function g, where g of x equal to 0 if x is all zeros, and it's 1 otherwise. Okay, so only if all n input bits are 0 does this function output 1, and otherwise it outputs all outputs. It outputs 0, otherwise it outputs 1. Meaning that once you put minus in the output bit, what it's doing is it's putting a phase of minus 1 on all those x's, on all x's except when x is all zeros. And then we again do a Hadamard transform over the first n qubits. Okay, so why does this work? Okay, so here's why it works. So let's try to understand it. So doing a reflection about the mean is the same as doing a reflection about, okay, here's intuitively what you want to do is a reflection about this uniform superposition over all x. Okay, so how would you do this? Well, what we do is we first move this uniform superposition to the all zeros vector. So we want to first do some transformation that maps u. We want to map it to the all zero string. So which transformation maps u to the all zero string? Well, of course, it's the Hadamard transform. So we first map u to the all zero string, and now we want to make sure that we do an inversion about 0. So how do you do an inversion about 0? Well, you use this transformation. So you use the transformation where you leave the all zero string alone, but you invert the phase of everything else. Right? You reflect everything else. Okay? So you do the Hadamard transform to transform this, and then you do a Hadamard transform back. Okay? Well, this is the intuition, but now let's see that this does the right thing. So you could write this as Hadamard transform times, well, you could write this as 2, 0 minus the identity matrix times the Hadamard transform. Okay, so what is this? This is the Hadamard transform times 2, 0, 0, 0, the Hadamard transform minus h identity h. But remember this, the Hadamard transform times itself is just the identity, so you just get the identity. And so, but what about this first term? How do we figure this out? So remember, what you know, if you try to multiply this out, remember the first row and column of the Hadamard matrix is just every entry is 1 over square root of capital N, right? And so if you multiply this out, what you get is you will multiply 1 over square root n times 1 over square root n times 2 for every entry. So you'll get a matrix which is 2 over n, where every entry is okay. So every entry is 2 over n minus the identity. Okay, so if you were to write out this transformation, it's 2 over n minus 1, 2 over n minus 1, and then every other entry is 2 over n. Okay. Okay, so now let's try to understand why this is a reflection about the mean. So remember what we're saying. We're saying that the Hadamard transform, the reflection about the mean is you do a Hadamard transform, you do this kind of phase inversion where you invert the phase of everything which is not the all zero string, and then you do the Hadamard transform again. Okay, and we are claiming that this operator if you work it out, it's to the diagonal. Every entry on the diagonal is 2 over n minus 1, and every other entry every off-diagonal entry is 2 over n. Okay. So now let's understand what this does if our input superposition is summation over x, alpha x, x. Okay, so we have alpha 0, alpha n minus 1. Okay, so what do we get? Well, what's the first entry going to be? Well, you'll get a 2 over n times alpha naught plus, so what's 2 over n times alpha naught plus 2 over n times alpha 1 plus alpha n minus 1? Well, this is just 2 times the average of these alphas, so it's 2 times mu. Right? So what's the first entry going to be? Well, you'll get 2 times mu minus alpha naught. What's the second entry? You'll again get 2 times mu, but now the minus 1 is in the second entry, so you'll get 2 times mu minus alpha 1, 2 times mu minus alpha n minus 1. So this gets mapped to summation over all x of 2 mu minus alpha sub x, x. This is exactly the inversion about the mean operation that we were looking for. Okay, so now we are all set to go. We understand how to do a reflection about the mean and how to do a phase inversion. Okay, so remember what our what we wanted to do in our implementation of the of Grover's algorithm was we first start off with an equal superposition. So remember these were the steps. So we first wish to start off with an equal superposition over all numbers from 0 to capital N, or in other words, over all the n-bit strings. So we do a Hadamard transform. So that's our initialization. Okay, so this is initialize. Then we want to do a phase reflection. So if this was x star, we want to take this and reflect it. Okay, so how do you do a phase reflection? Remember, so this is what does the phase inversion. Right? We feed in a minus in the answer bit and we compute u sub f. Right? Our quantum circuit for computing f. Then we want to do a inversion about the mean. And remember, our circuit for that was you do a Hadamard transform, then you do this, you have the circuit for checking whether the input is the all 0 string, and if not, then it outputs 1. But again, since our answer bit is a minus, that puts the answer in the phase. And then we do a Hadamard transform again to switch back into the standard basis. Okay, so when we do the inversion about the mean, that increases, so when we do the inversion about the mean, the amplitude of x star shoots up. And then we want to repeat these two steps over and over again. So we want to do a phase inversion and inversion about mean. Okay, and so that's what the circuit looks like. So we initialize, we do a phase inversion, inversion about the mean. Then we do a phase inversion again you do an inversion about the mean again, and so on and so on. So the circuit sort of gets extended out, and there are order square root of n such phases, right? So initialization followed by this circuit, this part of the circuit, phase inversion plus inversion about the mean, gets repeated order square root n times. And then you measure these first n qubits, and with probability at least a half, you get to see the needle. Okay, but with probability about a half, you may not get the needle. So what you do, you now take the outcome of your measurement and you look inside that entry. If it's marked, you're done. If not, you repeat this whole process again. Okay. One other observation about Grover's algorithm, which is that you have to get this number right. If you let Grover's algorithm run for too long, then it might uncompute the answer. So, it keeps going along. This keeps increasing in height. The amplitude of the needle keeps increasing in height. But eventually, and this is a good exercise for you to work out, you should check that the amplitude of the needle, after it attains its maximum value, it'll start reducing, and the amplitudes of these other entries will keep going up until the needle then becomes extremely unlikely. So one of the important things in Grover's algorithm is that you've got to set this parameter. So for example, if there were more than one marked items, then Grover's algorithm will run faster, but you will actually have to reduce this number of iterations appropriately. Okay, Grover's algorithm also is fairly general, even though it only gives a quadratic speedup, so it doesn't give an exponential speedup. But the trade-off is that it solves an extremely general problem. And this, the ideas behind Grover's algorithm have since been used in a number of different settings to solve a range of different kinds of problems. And so if you look in the notes, you'll find pointers to some other applications of Grover's algorithm.